Today we are tackling one of the most critical operational challenge in iron making, oxygen enrichment and the pressure paradox. Over the next 6 minutes we will uncover why increasing oxygen from 21% to 26%, it is not very specific to 21 to 26%, but it's overall it means to increase the oxygen from one level to other level, that is on the higher side. That doesn't just boost productivity, it fundamentally reshape the furnace, creating a cascade of thermal, chemical and aerodynamic changes that demand precise operator control. So let's dive deep into this subject. To understand oxygen enrichment, which is in the next slide, we need to grasp one fundamental concept, that is nitrogen is the ballast. In standard air 79% is nitrogen, chemically it's inert, it not participate in any hot metal making, it consume energy just being heated to combustion temperature, yet contributes nothing to reducing iron ore. So this means every ton of hot metal require a huge volume of gas, much of it dead weight. And a specific gas volume is the total gas generated per ton of product. By replacing that inert nitrogen with the active oxygen, we can burn the same amount of carbon and achieve the same reduction using far less total gas volume, which is also a philosophy after oxygen enrichment and production increase in blast furnace. So think of it as removing the dead weight from the furnace's gas envelope, more chemistry, less volume. This is the promise of the oxygen enrichment. That what we have just rephrased. So let me show you the maths. Considering 42 unit of carbon monoxide, scenario A, where it shows clearly a standard air which having a 21% oxygen. Now input 100 unit of air containing 21% oxygen and 79% nitrogen, output is 121 unit of wash gas. That is 21 oxygen will give you 42 CO and 79 nitrogen will be same as it is because it is not participating in any reaction. So total if we add on that 42 CO plus 79 nitrogen will be the output. Similarly, coming to scenario B, enrich blast, now we have gone up the oxygen to 25%. So input 84 unit of enrich air containing 21% oxygen and 63 nitrogen, output is 105 unit of wash gas, that is 42 CO plus 63 nitrogen. Now what is the result? A 13.2% reduction in a specific gas volume while delivering same oxygen. This 13.2% shrinkage opens a productivity window. The furnace can now burn more coke per hour without hitting the velocity ceiling that causes operational irregularities. That's the aerodynamic advantage of this oxygen enrichment. Now, so what does this mean for production? Oxygen enrichment is a proven intensifier. Even 1% increase in oxygen boosts productivity by 3 to 4%. And moving from 21 to 26%, that's a 5% increase translate to 15 to 20% production gain. So in practical terms, shifting to 26% oxygen enrichment increases your coke burning rate by roughly 24%. More coke burned per hour mean more iron produced per hour, directly improving furnace output. This is why steelmakers are so eager to adopt enrichment. The numbers are compelling, but and this is a critical. There is a hidden cost that emerges as you push towards 26%. Now coming to our next slides, which shows which talks about a tipping point, that is the aerodynamic impact of 26%. Here where things get interesting. Increasing oxygen from 21 to 26% represent a massive shift in furnace anatomy. Yes, you are reducing a specific gas volume by 13.2%, 13.2%. Yes, your productivity climbed to 15 to 20%. But the furnace doesn't see it that way. Instead of relaxing, it pressurizes. And this is the paradox. Less gas volume should mean lower pressure, but it doesn't. Why? Because the thermal and chemical changes triggered by that extra 5% oxygen create structural resistance that forces the furnace to push back against the blast. The furnace is essentially saying, I am not cooperating. To understand this rebellion, we need to look at the further heat. And more introspection is to be done. Every 1% increase in oxygen enrichment raises the raceway adiabatic temperature, and roughly this is around 50-degree approx. So if we are going up by 21 to 26%, that is the overall increment in the flame will be 265 degree in the hearth. The flame in the raceway doesn't get that hotter, they become intentionally dangerously hot. So this pushes the raft beyond a stable window of 2400 22 to 2400. What happened next is thermochemical chaos. At these extreme temperature, alkali gasify, potassium, sodium, silica, and all turn to vapor and ascend with the Bosch gas into cooler zones of the furnace. Now these volatile material then recondense into sticky viscous liquid, and that's when permeability collapse. I'll call this as a chemical clogging of these evaporating gases. It's invisible but devastating. Under extreme draft, alkali gasify in the hearth and are carried upward by the rising Bosch gas. As they encounter cooler zone between 800 and 1100 degrees centigrade, they are all condensed into sticky viscous solid that act like glue. Now these condensed phases trap fine ore particle and coke dust, clogging the void spaces between burden pieces immensely. So suddenly the open voids that were supposed to let gas flow freely become narrow, and it's a very clogging channels, and this result permeability issues, and permeability here crashes. There started a lot of spikes in the pressure. Operators see delta P increasing, differential it is beyond control between the 2 years, and the stack climbing 20 to 30% in a matter of hours. So this is invisible enemy of 26% enrichment. But chemical clogging is not the only problem. The cohesive zone, the region where the body soften and melt, is also reshaping. At 26% oxygen enrichment, the thermal gradient and increased chemical potential causes the cohesive zone to shift dramatically. It moves slower, becomes more compact, and stretches horizontally across the furnace width. Instead of a tall, narrow V shape that lets gas flow easily, it becomes a flat, doubly shaped band of softened burden that block the gases channel like a physical plug. The coke slit, those open pathway for the gas ascent, shrink and become very narrow. The flow resistance coefficient spikes. The gas cannot find a way through. So combined with the chemical clogging, this structural shift create a very very tough situation, and it reflect in terms of a rise in resistance. So operator face four operational levers. First, the raft, that is heat. If the hearth is too hot, you increase the steam in the blast or boost anything, pulverized coal like or steam act as a thermal break. So quenching the raft back to the safe window, that is 2200 to 2250 window. And second, top gas temperature. If the stack is too cold, you increase hot blast temperature to prevent moisture condensation and burden stickiness, and which causes also hanging. Third is the delta P. You open the center with a large strong coke pieces, creating a coke chimney that provide a low resistance escape route for the gases. And fourth is the liquid level. You increase tapping frequency to prevent liquid back pressure in the heart. These four levers must be orchestrated. So now coming to the practical opinion. Now here is the bottom line. If you don't increase permeability by roughly 25%, the furnace will fight you. The 4.1% volume increase from the enrichment will hit the resistance wall and trigger delta P spikes, breezing and slips. To achieve that 25% permeability boost, operator must 1. Open the center, use the bellowless top to charge strong large coke into the center, creating a high permeability gas escape route that bypasses the compact and cohesive zone. 2. Screen so increasing the screening efficiency to limit fines under 5 mm will be also a secret to achieve the success. The 26% environment has a zero tolerance for poor void fraction. 3. Apply thermal braking. Use blast moisture to quench raft back into the stable window and preventing excessive alkali recirculation. Oxygen enrichment is a powerful, but it demands a precision. Thus, by carefully controlling all those yardsticks, we can combat a slight increase of Bosch gas during oxygen enrichment by several levers. And once these our actions are compatible with this increase in Bosch gas, we will help in assimilating those increase in Bosch gas, and effectively the result of enrichment will be reflected in terms of production increase and stability of the furnace.